Bon après-midi tout le monde. Merci beaucoup Jean-François de m'avoir invité à parler. Okay, so I'm sorry. So I'm going to speak in English. Sorry. So I'm going to tell you some things of some of the work I've done, and with, of course, collaborators on trying to understand how cellular organelles are self-organized. So most of the work I will tell you about is a bit old because I haven't worked on this for a while, but hopefully at the end I will actually talk about some recent work which is unfinished, so either old stuff or unfinished stuff. Is this working? Yes. So the main body will be the work of two ex-PhD students, one of which is now at the University of Geneva, and the other one is now studying psychiatry. I guess he's interacting with me for too long. Gave him that idea. And then the last part will be a collaboration with old-time collaborator Matthew Turner from Warwick University, with a PhD student we share. And these two guys have people I've worked with on organelles for a while before. Right. And so here we're dealing with mostly eukaryotic cells, so cells that are compartmentalized with many kind of organelles. Here I will mostly be concerned about membrane-bound organelles, so little bags of membrane that are dynamically exchanging things. People talk a lot about membrane-less organelles these days, which are more like liquid drops. But here I really want to focus on membrane-bound organelles. Here you have numbers that show you that most of the membrane in the cell are actually inside the cell rather than at the periphery, although of course the cell membrane is a very important barrier. Most of the membranes are basically making barriers within the cell. And the one aspect that really interests me in this problem is the fact that everything is very dynamical. If you see this picture, you have the feeling that these organelles are stable and might be exchanging things, but in fact they are not stable at all. And here this is a sketch of roots that takes things from between the nucleus and the plasma membrane. So this is the outside of the cell. This is the cell center in some sense, the periphery. And this sketch is supposed to tell you that all these organelles are constantly exchanging things through vesicles that we just heard about. So either protein-coated vesicles like the one that Jean-François described, which take things from the endoplasmic reticulum towards the Golgi apparatus, and from the plasma membrane towards also the Golgi apparatus. And you have different kind of coats, which can do different kind of jobs. But also each organelle itself, or each compartment may evolve, may fuse with other compartments, may change biochemical identity by various ways. And so one interesting idea is to understand how this whole thing is organized and how does it manage to create well-defined roads or roots. And so the dynamics I will be interested in has mostly to do with vesicular exchange. So here this is a depiction of a vesicle budding from a compartment and fusing with another one. All this is mediated by proteins that are specialized and consume energy. And the other phenomenon is the fact that different compartments may fuse together and may also change color, meaning they may change their biochemical identity, the membrane, their composition mostly. Okay, and so if you want to understand how these roots are organized, you have, I guess, two point of views, many more, but two obvious point of views would be to say everything has to do with the tracks. The tracks are the microtubules, the vesicle walk on the microtubules, so you just organize the tracks and then the vesicle will follow. That's one approach. And the other approach is to forget everything about the tracks and just to say these things, they just diffuse around, they fuse and they scission and they exchange in ways that are completely controlled by their composition. And they do this in a sort of well-mixed manner where the tracks do not matter. So you've got many other possibilities here. I mostly want to focus on this one. I'm not interested with the tracks, but I'm sure they are also very important in some cases. So if you want to be able to organize something based on identity And considering that you have many types of organelles, you need many types of identities. And one possible candidate for these identities are proteins that basically mark different kind of membranes. So here you have the distribution of a particular kind of protein family, which is called the Rab family. So Bruno Good is not here today, but he's an expert in some kind of Rabs. And so the Rab, these are GTPases, which means that they can be passive in the cytosol or active in the membrane, and they cycle between these two states by consuming energy, GTP. This is depicted here. They influence many aspects of transport. They influence budding, transport, and fusion. And as you can see in this map here, you have different Rabs in different places. So for instance, the endosomes, which are basically the place where endocytic material comes in, they are labeled as early endosome and late endosome, and early is Rab5, late is Rab7, these sort of things. Within the Golgi apparatus, which has an entry phase and an exit phase, these different phases are labeled by different Rabs. So this is all very complicated in my kind of models, because I'm mostly going to talk about concepts. These are just going to be colors. But you can think that there are many colors and many combinations of interaction between colors that could self-organize these things. So let's look at the dynamics a little bit. So we can start by looking at the endosome. So again, the endosome is the sort of first compartments that are populated by whatever comes from the outside. So endocytosis is a process by which the cell ingests things. And then this endocytic material comes into the early endosomes. And then these early endosomes, they evolve towards late endosomes. And so this is actually a work done in Marino Zerial's lab, which was here a few weeks ago to give a talk on something else. And so you can follow one of these compartments, which starts as very small, early endosome. So it would be marked with these Rab5 molecules, and then it would little by little evolve towards being a late endosome, so marked by a Rab7. This is the radius of one of these dots here, one of these cisternae. And you can see that the radius, it grows in time, and then it stays to some sort of steady state size. And this is in seconds, so you have an idea of what dynamics we have here. And here you can see the composition of this object. So it's the composition of in Rab5. So the composition in the early label. So at the beginning, it's mostly an early endosome because the early label varies as the size, but then eventually you see there are a lot of very large fluctuations that makes this thing jump because obviously something else fused with this little bag. So here the size and the composition increases, but then the composition decreases, then it increases again, and eventually at the end it goes to 0, which means that this thing is not an early endosome anymore, it has become a late endosome. And so basically the idea is that very dynamical, very strong fluctuations, and so some sort of steady state, but large fluctuation around the steady state. That's the example for the endosomes. Now, we can also talk about the Golgi apparatus, which is a fascinating organelle as far as I'm concerned, mostly because of its structure. So here, Jean-François told us about the endoplasmic reticulum, which is this yellow thing here. And this is an endoplasmic reticulum exit site where things are secreted from the endoplasmic reticulum. And they are secreted through small vesicles. So all these things here are small vesicles, 50 nanometer in size, roughly. And these small vesicles, they will fuse with each other, they will fuse with some organelle called the Golgi apparatus, which itself is made of different stacks of basically sort of bags, which are called cisternae, which are very flat, spherical-like objects. Depending on the cell, the structure can be very different. In yeast, for instance, some yeast, in Cerevisiae, the different stacks, they are dispersed all around the cytoplasm. In other kind of yeast, these cisternae, they form mini stacks. In plant cell as well. In mammalian cell, often they form very large stack, but it's well-defined stack. So it's a structure that is quite well-defined at steady state. Here you have another example. This is in a plant cell. It's amazingly regular. Maybe Jacques would call that a smectic. I don't know. I guess probably. It's really incredible how this structure managed to exist because all these objects are completely floppy. They are very, very flexible. So obviously they are tied to, they are packed together. There's adhesion. There's a lot of things going on. And the other thing that's interesting is that if you were to follow one molecule, it would basically go through this stack. All the molecules that compose this stack are gone within, I don't know, 10, 20 minutes. And so it's a steady state structure, but all the components are exiting the structure. Here, this is an example of a yeast Golgi. So as I said, the cisternae are dispersed. And in this case, you can follow one cisternae, and you have two colors here. One color is early, meaning the color of the entry bags, and the other is late, the color of the exit bags. And you can see that one bag is going from early to late identity, in this case, within 1 minute. So in this sort of mammalian cells, the transit time of proteins through this stack is about 20 minutes. Here in yeast, it's more about 1 minute. So there's a different time scale. All right. So let's have a look at how we might want to try to describe this. And in this first part, although this is definitely the most fascinating aspect, I will not talk about structure at all. I will just want to talk about interactions and transport within this system, but I won't, because I don't know how to really, I won't really address the fact that it's a very beautiful stack. All right, so let's consider a bunch of vesicles, a bunch of compartments, which can have different kind of dynamics. They can fuse together. They can also emit new compartments, let's say vesicles, by budding, as we just saw in Jean-François's lecture. And let's see what sort of size distribution one might have. So if the fusion, of course, makes things bigger and the budding makes things smaller. And if you say that the fusion happens randomly through diffusion and that the budding increases with the size of the compartment, then you expect to have a steady state size when fusion balance budding that gives you a size. And it's roughly the fusion rate over the budding rate. If you want to attack this from a theoretical point of view, you can write a master equation. We've had many examples of a master equation in Jean-François's lecture before. So we have a parameter, the fusion rate, the budding rate. We have a total amount of material in our system that's closed the system. So the total amount of material is going to be distributed among objects of different size. The size is n here. Each material has n unit size, and the total mass is this. And you write a master equation by basically looking at how the amount of bags of size n would vary in time. It varies because of fusion, and it varies because of budding. And basically, fusion of two smaller things make a bigger things, and fusion of the bigger things with something else makes it go away. This is what this says, and same thing for budding. And you obviously have to pay attention to what happens with the vesicles, which are the unit size, and the unit size, they are created when anything buds. All right, so if you try to work out the steady state of this, so when it doesn't vary in time, you have a characteristic size, which is the total mass times the fusion rate divided by the budding rate. That gives you the characteristic size, which corresponds to the steady state size. And you can look at the size distribution, and the size distribution is not peaked. You don't have compartments that are mostly all of the same size, but you have a very broad size distribution. It's typically a power law with an exponential cutoff that corresponds to this typical size. This is the sort of things you get. So you have many, many small compartments, very few large ones, exponentially few large ones, and the average size is given by a ratio of fusion over budding. And this is mostly due, it's a kind of mean field argument if the system is very, very large. But now, if the system is not very, very large, for instance, if the total the average size is predicted to be equal to this, but if this is larger than 1, then it would be predicted to be larger than the whole mass in the system, which is not possible. So in this case, what happens is that basically you form one big compartment, which takes most of the mass, and you have a distribution of smaller compartments like this. So this is a finite size effect of the master equation. All right, so this is what happens if you have one kind of components distributed into vesicles that can fuse and bud. And in fact, this is actually something that you can observe in many kind of system in the cell. This is the size distribution of endosomes, so the power law is not completely obvious here, but it's still over a couple of decades that you can see a power law. Here, this is a completely different thing. These are the distribution of integrin clusters between two cells. So integrins are Caderins are what makes the adhesion between cells. They are molecules, this cadherin cluster, and they form clusters which have dynamics that are a little bit similar. They fuse, they undergo scission, and you can, in this case, see a very beautiful power law with an exponential decay. So this description is quite basic and can actually describe a lot of interesting things. All right. So now what I want to look at is what happens if you have different kind of component. Let's say, okay, so this is a distribution of the types of lipid you have in a cell. The idea of this is just to tell you that there's many kind of lipids and you find them in different places and they are not mixed together. Okay. So in this case, you need to be able to sort the lipids and to put some lipid in some place and other in other places. And how can you do this? One way you could do this is if you have a mixed compartment, you can have the compartment demix by having vesicles that take preferentially some color and other colors, and then these vesicles can fuse in a way that is called homotypic, which means that the yellow vesicle they want to fuse with the yellow compartment, but not with red compartments. If you do these sort of things, it's basically a sort of active equivalent of phase separation, where components that don't like each other would phase separate, except it's not thermodynamic equilibrium. It's based purely on transport, and the don't like each other comes from the fact that they don't want to fuse together. Okay, so if I'm not mistaken, Jean-François, next week you will tell us about a simple model that explains how this can happen. And the basic idea is that you need composition-dependent fusion, so I won't talk about this. What I want to talk about is how this vesicular, identity-specific vesiculation can separate things and how fast can that happen. So these are very simple stochastic models of how vesicle can sort things. So here you consider a compartment which has mixed A and B's. And let's say you can have both A and B vesiculate, but let's just say that only B can vesiculate with some rate. This is the budding rate K. And B can then fuse back with a fusion rate K fusion. And if you make this fusion rate dependent on the composition here, and in particular, if you say that if there is no B in this compartment, the B will not fuse with it, this means that basically this is a specific fusion, then at some point you will have removed all the B's from this compartment, and then the A's and B's will remain separated forever because they don't want to fuse together. And the question is, I mean, at least one question here is, how long does this take? So how long does it take to separate components based on specific vesiculation and fusion if they are mixed before? And so this is an example of a simulation of the process. So you start with a system which is half B and half A. And little by little, you bud B's off, so the B composition decreases, and then you fuse back, it decreases, etc. So budding basically removes B's and fusion brings B back. And at some point, you will hit this position when there's no B anymore and you've separated your system, they will never mix again. And you can calculate this as a sort of first passage time problem, as again we heard about last week or the week before. And so if you look at the amount of B material, it goes down, and each time it fuses, you reset it to, I mean, in some simple version, it's like a resetting problem where the B composition decreases, and then when you have fusion, it goes back to zero, and you have to ask how long do you have to wait for this to happen. And there are two limits, which are well defined. One limit is if budding is much faster than fusion, and in this case, all you need to wait is budding. Budding separates things. Fusion is irrelevant, so as basically the separation time is given by budding. The other limit is when fusion is important, and then in this case it becomes much, much harder to phase separate because each time you bud, then you fuse back, and it turns out to be exponential in the ratio of the fusion over the budding rate. So you have these two very well-defined limits, which basically separates fast sorting and slow sorting based on how much do you fuse. And so basically, so what you can see, if you go back also to the initial, the previous discussion where we saw that if you don't have a lot of fusion, you have a lot of small compartments, and if you have fusion, you can make large compartments. This means that if you have two components and you want to separate them, either fusion is very weak and you will separate them, but you will have only very, very small compartments, or fusion is strong, and you will take a very long time to separate them, but you can end up with large compartments. So you have this trade-off between fast sorting and having large compartments, which is basically a stochastic effect in this kind of context. All right, and so does this say anything to anything happening in cells? So we can look at what happens if you make the Golgi disappear. You can use drugs that make the Golgi fuse back with the endoplasmic reticulum. These drugs are called, for instance, BFA, bovine, I can't remember what is BFA. But if you add BFA to a cell, I don't exactly remember what happened, what it does, but it makes the Golgi completely fuse back with the endoplasmic reticulum. And then you wash out, and the Golgi will form after a while. And this is how much you have to wait. You have to wait tens of 20 minutes to reform the Golgi. And during that time, the endoplasmic reticulum is vesiculating a lot of vesicles. So it's actually vesiculating much more vesicles than you would need to form a Golgi, which means that the time you need to wait to reform the Golgi is much longer than the time you need to extract Golgi material from the ER. And we argue that this is because there is a kinetic barrier, which is due to fusion. So basically, vesiculate Golgi out of the ER, but fusion, since the ER is now a lot of Golgi-like, because the Golgi has fused with it, this vesicle will fuse back with the ER before they can nucleate a new Golgi, which is why it might take such a long time. Okay, so that's an example where this can be important. Okay, so now let's have a look at some other process, which is biochemical maturation. So as I told you, if you look at one compartment of the Golgi of a yeast, which is separated, you can see that it goes from an early identity to a late identity, in this case in a few minutes. And this, so what these colors mean is they have to do with the Rab, in this case, these are the Rab molecules. So basically, the Rab molecules exchange each other. I told you that a Rab molecule is cycling between cytosolic and membrane states, consuming energy. And it so happens that this cycling is cooperative, which means that if you have a lot of pink Rab on a membrane, a new pink Rab is more likely to come. And so this leads to this maturation process. If you start with only green Rabs, then the green Rab will remain for a while. But as soon as enough pink Rab come to this membrane, then the whole thing will turn into a pink identity. Okay, and here you can also ask some basic questions about sorting and maturation. So maturation, what it does is that it mixes things. If you start with a white compartment and then you make it maturate to a black compartment, for a while it will be gray, so it's mixed. Vesicular budding can sort things, because if you bud white and black vesicles separately, you will sort them out. And so the question is how these two processes interact. And you can think of two things. If you imagine that you have a source of white material, that the white is turning black, and you have a sink of black material, two kinds of steady state are possible. One is that you have a mixed compartment in the middle. The white vesicle, they mix with the grayish compartment, they turn black, and the black vesicle bud out and go to the sink. This is if the sorting is fast, which means that if you manage to, if this compartment can remain white enough so that white vesicle want to fuse with it. On the other hand, if maturation is much faster, when you create a compartment, it will turn into a very dark gray fast, so that the white doesn't want to fuse with it anymore. And in this case, you don't really have a steady state. What you have is compartments that evolve independently from the others by just maturing and growing and then exiting the system. And so this is the sort of model we will study. We look at one compartment. It receives A molecules, A turn to B, and then it emits B molecules. And whenever there is no more A molecule in this compartment, then the new A molecule cannot fuse with it, and this compartment is isolated. So this is another kind of stochastic system we can study, and these are the typical simulation that we can make. They look a lot like the other ones, but it's actually a completely different system. Here you grow because you receive A molecules, and the number of A molecules decrease because of maturation, and then the B, they leave. But you also have this particular time at which the compartment has completely maturated into a B compartment, and the flux doesn't go to it anymore. And this is quite actually similar, reminiscent to what happens in the dynamics of these early endosomes. So the early endosomes, they grow by fusion. They decay, at least the amount of early identity decay by maturation, and at some point they turn into late endosomes. So this dynamics is quite similar. And in fact, you can see peaks, even some sort of periodicity that is also present there for reasons that maybe I'll get into. Okay, so how do we quantify this? We quantify this by looking at what we call the output parameter, which is what fraction of the total outflux is into vesicles as compared as into fully maturated compartments. So the total outflux is the amount of vesicle and the amount of mature compartment that leave, and you look at the ratio of the number of vesicle over this, which is necessarily smaller than 1, and which is 1 if you have a pure steady state where this thing always exists and basically receives gray vesicles and spits out black vesicles. Okay, so first you can look at a steady state. The steady state equation would give you something like this. So influx balanced by maturation for the A component, maturation balanced by budding for the B components, and the steady state always have a solution. So you always have a steady state, which means that this compartment at steady state always exists. But if you look now at stochastic effect, which can lead to the full maturation of a compartment, this will actually deviate a lot from the steady state, because this is by definition a state that does not accept influx anymore. And so you can ask again how much time you need to go to that extent. And this is quantified by an equation which is like a first mean first passage time equation, like we heard about in Jean-François's lecture a couple of weeks ago. And you can calculate it, and it looks like this. So here the parameters are the influx and the maturation rate. And the first passage time to isolation looks like this, and it has two very well-defined limits. One is if the maturation rate is fast, in which case it's basically equal to the inverse of the maturation rate. The other one is that if the maturation rate is slow, and then it's exponential. So it's a little bit like the other thing for sorting, except that here it's maturation, so we're comparing maturation and influx, and we also have a difference between a sort of linear system that maturates linearly and a system that is more controlled by the influx and that then is exponentially slow to maturate. And this is quantified here. All right, and so now you can actually understand a little bit of this really funny stochastic dynamics by looking at the trajectory in the phase space. So this is again the mean field equations. And this is the amount of A in your compartment and the amount of B in your compartment, and that's the steady state here. And you start here, you start with, let's say, one just vesicle of A. And these are the trajectories followed by this mean field equation. So if you just take the simple one, when the influx is constant, you just go straight to the steady state. If you add some more complicated things, like if you add homotypic fusion, so that the influx depends on the composition, and if you also add something like cooperative maturation, which is a sort of feedback loop on maturation, you maturate faster if your neighbors are maturated, then you can get these sort of trajectories which do this overdamped dynamics. And here they go very close to the boundary where you have fully matured. And so basically, these sort of fluctuations, you can understand them as fluctuations, as basically trajectories in the phase space. Right, so that's it. So these are, here I wanted to give you the two ingredients, or three ingredients, let's say, that I'm going to put in my very big, or not big, but complicated model of some sort of model of the Golgi apparatus. Initially, this model, we build it to answer this question, which is how do things move in the Golgi apparatus? This is like a 50-year-old question that does not really have a definite answer. Jean-François mentioned it in his first lecture, I think. And the question, so the Golgi apparatus is a stacked system. It has an entry phase called the cis phase and an exit phase called the trans phase, and things move from the cis to the trans. How do they move? Two sort of schools. I would almost call them church, because it a little bit looks like people who believe in one cannot believe in the other one. One is that the compartments are stable and vesicles go from one compartment to the next. This is called the vesicular transport model. The other one is that the compartments themselves are evolving over time. They are maturating or maturing. They are changing color. But then in this case, since some proteins remain in the stack, those proteins must be transported backward by vesicles, so otherwise they would leave the stack. And so these two pictures give you very different predictions or conclusions or whatever regarding whether vesicles are transported in an anterograde fashion or in a retrograde fashion. And people are fighting over this for ages. And so we thought that we would just try to make models of this. And this is the model. It's a very simple model in the sense that there is no space, there's no stacks, there's no adhesion, there's no mechanics, there's nothing like this. All we have is 3 identity, because we have cis, medial, and trans, just to sort of reflect the Golgi. And we have the different recipes or the different rules that I told you about before. Homotypic fusion, blue fuse with blue, but not with orange or green. Specific budding, so the blue and the red and the green or the orange are budded in different vesicles. And maturation, the blue can maturate into a yellow and yellow into a green. And that's it. And we have 2 phases. This is sort of the ER, or the cis phase, or the entry. And this is the exit, which is trans-Golgi network, or basically the exit. All right. And so again, no space, no mechanics, no molecules, just kinetics of exchange and all this. And I just put this here because when you see the images of the Golgi, you must say space is hugely important, it's very well organized, it's just a beautiful stack. But in fact, what you can do is you can disrupt this by making Golgi cystine adhere to mitochondria. And this is what they have done in this paper. And so each of these white stuff is a Golgi cystine, which is now completely dispersed, and it's stuck into mitochondria. And in these cells, transport still works, which means that somehow the stack is not essential to transport, and transport still works in the right direction. So directionality and stacking are not equivalent. Interesting. So we make this model. Okay, so again, we have this homotypic fusion. We have a fusion rate, we have different kind of budding. Rules have some details, but it's not really important. We have 12 parameters about, but we simplify them into 5 parameters because we normalize them and we take the maturation rate to be the same between the different things, the fusion and all this, and so we end up with 5 parameters. And so the really important, so everything is normalized by the fusion rate. So we have an influx that's going to tell us how big our system is. We have maturation and budding, these are the 2 really important ones, and then how you fuse with the boundaries are less important. And I will show you a couple of snapshots of simulations, so you will see a bunch of balls. The size of the ball is how big the cystine is, how many vesicles, and the color tells you the composition. If it's blue, it means that it's an early one. If it's red, it's a medial one. If it's green, it's a late one, and if it's sort of darkish, it's somewhere in the middle in terms of composition. Let's start with a very low budding rate. So you fuse things together, but you don't bud them out. You end up with large compartments, and they are pretty black. It means that budding is needed for sorting. You don't bud, you don't sort, you have large compartments, they are black. This is not really what's happening, apparently. Intermediate budding rates, compartments are smaller because they decrease in size because of the budding, but you see that they are very well defined, pretty well defined in colors. So this is a way to actually get compartments that have a well-defined identity. If you bud a lot, if you bud very fast, then you only have vesicles. They are obviously of a single color because of the rules, but it's just vesicles, so these are not compartments, really. Okay, so we can make phase diagrams. So here we've got the budding rate, the maturation rate. This is the purity, how far you're from the center. And this is the size. Again, it's a distribution, so the size is a characteristic size here. And these are the phase diagrams that we get. So here in the purity phase diagram, we have a nice boundary between something that is very pure and something that is very mixed. And it has to do with the budding rate. It's actually a linear boundary where the budding rate is equal to maturation rate, which goes back to what we said before. If you maturate faster than you bud, then you are not then you're mixed. And if you bud faster than you maturate, then you can be well sorted. As far as the size is concerned, the maturation rate is not really important. What really matters is the budding rate, because if you bud a lot, you get smaller. And now we can say that if your goal is to make something that would look like a Golgi, let's say, with well-defined cisternae that are big enough and that have well-defined identity, you need to be somewhere in the middle. You need, at the same time, to have large compartments and well-sorted. You need a budding rate, which is of the order of maturation rate, which is also of the order of the fusion rate. So all these rates must be roughly of the same kind. So we have explanation for all these boundaries, which I probably won't get into. Now let's look at the transport, because this was the original question. All right, so we quantify transport by looking at one vesicle. It leaves a compartment and it gets to another one, and we're quantifying the difference in composition between the compartment it joins and the compartment it comes from. And if a vesicle mostly goes from something early to something later, we call it anterograde transport. It doesn't mean that it goes spatially in one direction. It's in the space of identity that it's anterograde. And this is the sort of thing that we get. So here we're varying the budding rate. This is what the purity looks like as function of the budding rate. That's the previous phase diagram. The size go down if you increase this way. And this is the average flux, let's say the enrichment parameter. So here, as you can see, the enrichment towards the cis phase is much large, is positive, and the enrichment toward the trans phase is negative, which means that vesicles are going in the retrograde fashion. In this limit, vesicles are going in the retrograde fashion. In these other limits, where the cisternae are very pure, vesicles are going in an anterograde fashion. Which is funny is that somewhere in the middle, they're actually going in the centripetal fashion. They're going towards the medial identity, which nobody really discussed before. So that's, I think what I like about this is that I'm just having a very conceptual model. I'm changing one parameter and I go from one church to the other just by changing this parameter. And we can actually understand pretty well what's going on based on the idea that I told you about before. So maturation is, if maturation is fast, I'm over here, or if budding is slower than maturation, then if I look at one component, this component is maturating very fast, and so the contaminating species, the species that is a minority, is the one that has not maturated yet. And so when this one buds, it will bud back with an early compartment, while if the maturating vesicle buds, it goes back to the same compartment, so there's no transport. And so this is why here you're going retrograde. If in the other limits, it's exactly the opposite, and you're going anterograde. And in the centripetal, it's a bit more complicated, but basically, in this case, you have transient medial compartment that exists, and vesicles tend to go towards this compartment. So that's our explanation, or our way to solve the vesicle transport problem, is to say that it can go either way, depending on the parameters, which I guess is a theorist answer always. Interestingly, if you prevent compartment to fuse together now, you still have the same sort of retrograde to anterograde transition, but in this case, you don't have the centripetal regime anymore because you don't have medial compartment. Medial compartment only come from the fact that compartment can fuse with one another. All right, so basically the bottom line here is that this is our phase diagram. You can explore the phase diagram by changing this parameter, the budding or the maturation. And now we can stick our neck out and say, yeast maturation is fast, mammalian cells maturation is much slower, and so you could imagine that yeast would be somewhere in here, and the mammalians would be somewhere in there, and so the mammalian would be in the sorted regime, and the yeast would be in the mixed maturating regime. Of course, this is very simplified, but why not? We can say something like this. All right, so this is the summary of that part. So first, if you want to sort things by vesicular transport and fusion, you need specific fusion. But if fusion is fast, it will take a very long time to sort things, and if fusion is low, you will have very small compartments. For maturation, it's a little bit the same thing. If you maturate fast, you mix things, and it will be, so maturation is a mixing component, and budding is a sorting component. And you can have different kind of organization, different kind of vesicular transport by changing these two parameters. All right. So now I'm going to move to this one, and this one is the first time I talk about it. It's very new, so let's see what you think of it. And it's very nice that Jean-François mentioned all these funky structures in the endoplasmic reticulum just a few minutes ago, because I want to talk about funky structure in the Golgi apparatus. And so again, so the same sort of picture for the Golgi apparatus. And then if you look at this is the Golgi, and this is what is called the trans-Golgi network, which is whatever things go to when they leave the Golgi before they're going somewhere else. And this is, of course, a cut through something that actually looks a little bit like this. It looks like a sponge phase, basically. There's a lot of holes. If you look at the Golgi cisternae in a little more details, this is in some plant cells. Yes. Some algae. You can see that there's a lot of holes in this, especially in the late cisternae, there's a lot of holes. And I've got a lot of pictures like this. I've got more pictures here. Look, this is the trans-Golgi network. This is an amazingly spongy phase with a lot of holes. This is actually the cis phase, which has also, it's very non-spherical, basically, in terms of topology. Got many examples here. And so, can we say something about topology? So then we can have our membrane mechanics slide, which I think you probably already mentioned. So if you want to characterize a membrane, which since it's a two-dimensional object, you need two curvatures. And you can also characterize it by their mean curvature, which is the sum of the two, and the Gaussian curvature, which is the product of the two. And typically spheres, they have spheres, the two curvature is the same value, and their mean curvature is 2 over the radius. And the Gaussian curvature is positive because the two principal curvatures have the same sign. For a saddle, the two curvatures, principal curvature, have opposite sign, or they don't have to be, but at least, opposite sign, and the Gaussian curvature is negative. And then you have this topology theorem, the Gauss-Bonnet theorem, which tells you that if you integrate the Gaussian curvature over a closed area, you get a constant value regardless of the shape, provided that you don't change the topology, and the value is the number of handles or holes you have in your structure. And so if I take a sphere, I push on it in any ways, I deform it, I am not changing this integral. All right, and so now how do you quantify the shapes of membranes? You write an elastic energy, which is the Helfrich energy, which has a term that has to do with the mean curvature squared, could have a spontaneous curvature as well, times a mean bending modulus. And then you have a term which is proportional to the Gaussian curvature times the Gaussian modulus. And this term often is removed because of that property. If you don't create holes, then you don't need to care about this because it's a constant. You can push on it. You don't change that contribution. That's only true if this modulus is uniform, by the way. If you have a membrane with different components and the modulus can change in space, then you have to consider this term as well. Okay, so the energy of a sphere, it looks like this, and the energy of a saddle, if you consider that the saddle has no mean curvature, it's like this, okay? And so if your modulus of Gaussian curvature is positive, you want to make sponges. You basically want to increase the, we have to get that right. Yes, that's right, it's okay. So you want to make as many holes as possible because each time you make a hole, you gain energy if your Gaussian modulus is positive. If it's negative, you don't. And so if you want to consider a saddle or a sponge face, let's say, you need to consider higher order in this curvature in order to stabilize your system. And one possible way to do it is to add another term which would be as a Gaussian curvature squared, which is rarely discussed because this term is really rarely considered in the membrane mechanics literature. But if you want to consider it, then if you want to stabilize a phase like this, you need to add something like this. And then you have optimal Gaussian curvature, which would be the ratio of these two parameters. And this is the energy of a sponge phase as a function of the number of holes you have in it. So you can make more and more holes, but your holes now have a limited, you can not make infinitely many holes because they are limited by this stabilizing factor. All right, so can we have a positive Gaussian curvature modulus? The answer for pure lipid membrane is no. It's always negative, at least as far as it has been measured so far, which means that if you have a pure lipid vesicle, it would not spontaneously want to make holes. On the other hand, if you add proteins to it, then it is possible, if the proteins have the right shape, like they curve in one way and they curve in the other direction the other way, then they certainly can contribute to an effective positive Gaussian curvature modulus. And actually you can do simulations where you see that proteins in some ways, like sort of banana shape, proteins can spontaneously form holes spontaneously form holes in vesicles. So it's possible. All right. So then, if you have such a membrane which is mixed with components that want to make sphere, we call them sphere-loving and saddle-loving components, then you would have to describe their energy as a function of the composition by saying, for instance, that your Gaussian curvature modulus depends on the composition. It has a part that is negative, that is the sphere-loving component. Oh no, this is the saddle-loving. So a part that is positive, and a part that is negative, and phi is the amount of this greenish stuff that want to make saddle. Okay? And so here we want to be in that situation where there are actually stuff that want to make sponges in the membrane. And then if you imagine having vesicles budding off these membranes, the vesicles, they will not take these green components because these green components don't like sphere, they like saddles. So the vesicle will be enriched in the dark components, which means that this membrane will get enriched in the saddle-loving components. The more you bud things off, the more this membrane becomes enriched in saddle-loving. And at some point, it might phase separate. This is the composition of the vesicle as a function of the membrane composition for the different values of this energy, which is written here, that tells you how much the green stuff don't like spheres, something like this. So the idea is that if you take a membrane and you somehow have saddle-loving components in this membrane, the more you bud vesicle of this membrane, the more it gets enriched into these saddle-loving components. Can it phase separate? So in order to know whether this membrane can phase separate into a sphere and a sponge phase, it's going to be very simple. They should be interfaces, which we don't consider. We just say, let's write this energy as the energy of a sphere times its composition, the energy of a sponge, which we just calculated, some entropy of mixing, and some conservation of both the pink and the dark and the green. And we just minimize this energy. And what you find, the entropy is written as an ideal gas entropy. And what you find is that you can phase separate if these two guys are different enough, which means if how much the green guys hate the sphere or how much the dark guy hates the saddle is large enough. You can have something that looks like a common tangent construction, which I don't really need to get into, and you end up with a spinal curve, which looks like this. So here I have the system composition as usual, and here, in this case, I'm varying this nonlinear parameter, but it doesn't really matter. What I'm varying how much energy is gained when some component that likes saddle goes into a handle. That's basically this. This is this axis. Could also be the temperature, whatever you want. And so this is the spindle. These are different parameters. If you are somewhere in here, you want to mix your system into a spherical topology and a sponge-like topology. And actually, the criteria has to do with how much energy is gained by one of these proteins that likes saddle, and it depends on this area, the area of the protein, the area of the handle, some of the elastic parameters, and it's actually the same sort of criteria that tells you whether proteins can be sorted by mean curvature. So I guess, Patricia, you might talk about this next week. So proteins can be sorted by mean curvature. This is a well-known fact. Here we argue that protein might be sorted by Gaussian curvature as well, and they might create a phase transition. All right. So, okay, so now let's look at an open system. So an open system with influx and outflux. So I have an influx with some composition of these saddle-loving components. I have an outflux. The outflux is going to be due to vesiculation. So the composition of the vesicle is something that comes from some thermodynamic sorting process, except that now it's sorting by curvature or by the absence of Gaussian curvature, by Gaussian curvature rather. And I can ask, okay, so what's my steady state? And can my steady state be phase separated? And we can write equations for this, and the answer is you could have a phase. So the problem here is that at steady state, the outflux is equal to the influx, both in terms of area and in terms of composition of phi. And so if you want this to happen, what you need is that the composition of the vesicle coming out must be equal to the composition of the vesicle coming in. This is a requirement to have a steady state. Now, if you look at so in a system where I can vary my membrane composition without phase separation, the composition of the vesicle reflects the composition of the membrane they come from. Of course, they don't want to go in the vesicle, so it's lower. But eventually, you know, whatever composition of your vesicle you want, you will find a membrane composition that satisfies this. This is if you don't have phase separation. If you have phase separation now, during the phase separation, the two phases are have the same chemical potential, and as you change the amount of the two phases, the chemical potential remains the same. It's always given by this line here, which means that the vesicle composition, it looks like this. In the spherical region, it increases with the composition of the compartment, but during the transition, it's fixed at a particular composition, which is the vesicle composition that corresponds to that chemical potential. And so if you want to have an open system that would be phase separated, you need the influx composition to be exactly this one, which requires fine-tuning, which is not very realistic. It's possible, but it's not realistic. All right, so that doesn't seem so easy to get phase separation this way. So now, can we consider something else? We are going now to consider a stack. So here the idea is the following. Let's say that from the ER, you create a cisternae. It's a cisternae that has some amount of sphere-loving and saddle-loving things in it. And then this cisternae, it's going to exchange, by vesicular exchange, it's going to exchange things with other cisternae. In this case, we consider a stack. So each cisternae exchanges with its neighbor. There are some rules to be given, but they are not that crucial. So here we're saying that cisternae, there's a leakage of vesicle, there is a transport in anterograde fashion and retrograde fashion, but all these vesicles, they will be sorting sphere-loving component. And so as vesiculation happens, this guy will be enriched in saddle-loving component. And at some point, it will hit the phase separation system where it wants to become a purely sponge phase, just like this one. And so the idea here is that this transition will give you the length of the stack. The length of the stack is fixed by the fact that at some point, your compartment wants to be a saddle. It will turn into a saddle, and it will join the TGN, Trans-Golgi network, which is a big saddle, or a big sponge. This is what we're saying. Okay, so to make the story short, we can write transport equations. So they look, again, like diffusion advection equation with some leakage. Here, in this case, the advection comes from the fact that the anterograde and retrograde flux might be different, but also from the fact that each time you create a new vesicle, you push the others away. This is sort of maturation mechanism. And we get this sort of profile. So this is the size tells you how big the cisternae is, and the composition in terms of phi tells you how close it is to becoming a sponge. And so obviously, okay, so it's possible you can get a steady state this way. It's a well-defined steady state, and the length will mostly be given by the fact that you turn into a sponge because you vesiculate a lot. Okay, and you can make this model even more self-consistent by saying that cisternae generation actually comes from the phase separation of another sponge phase. So here we're saying that the Golgi is flanked by two sponge phases. One is what is called the ergic, ER to Golgi intermediate compartment, and the other one is the TGN, Trans-Golgi network. And if you look at this, it does look a little bit like those two things flanking the Golgi are not at all spherical topology. So we do this. We say that you have an influx into this ergic coming from the ER. This influx will lead to phase separation, and you will be creating a spherical topology compartment which eventually gets cut after some time, so it's a parameter, the cutting time. Then this compartment enters the stack and starts exchanging with the others. And when it becomes a sponge phase again, because of vesicular sorting, it turns into the TGN. We can study a lot of things. We don't want to get into the details, but basically you can have a steady state like this. It obeys some rules, so basically you need the cutting time to be not too large, the influx to be not too small, things like this, but it's possible. Since I only have 5 minutes left and I want to leave room for question, I'm just going to go to the very quick summary of that part. So here, what I want to propose, I'm not saying it's the truth, it's just interesting to think about it. I want to go beyond the sort of spherical topology idea, and I want to consider the possibility of a topological transition between a sphere-like and a sponge-like structure mediated by vesicular sorting. And we can imagine such a phase separation and phase coexistence at thermal equilibrium. Of course, there are energy barriers, which could be very large, so we haven't looked at this. You could create a steady-state stack structure whose size would be limited by the fact that as it progresses, vesicular sorting creates a sponge-like structure. And you can have a self-consistent model by saying that both system A generation and system A disappearance proceeds through phase separation between spheres and sponge phase. That's my story. Thank you for your attention. And if you have any question,